Okay, thank you. And thank you for giving me the opportunity to speak here. I'll try to keep it brief because dinner's coming up, but I'm probably not going to succeed. So I'll see how much I can get out of the chairman. So this is a topic which was started by Professor Youngmin Cho when he happened to meet with me at a conference a few years ago. And he asked me to do a lattice simulation to take a look at some of the calculations that he was doing, and in particular, which he was going to present today if he unfortunately wasn't able to attend a conference, so he couldn't. I should also mention Professor Cundy and his collaborators at KEK who have done some similar work, which is not quite the same as what I'm doing, but they were very useful to me to help me understand the theory from their papers. So let's start by quickly mentioning confinement. As I'm sure you know, Quark confinement is one of the big issues in QCD, not yet shown. But two models which I'd say are probably dominant. Firstly, a dual Meissner effect. So magnetic monopoles playing the role of the electrons in the superconductor. Secondly, people are also keen on a center vortex model. It's caused by center symmetry, generated by the center symmetry in QCD. So in this talk, I will propose something a little bit different from either of these. Just to give you a quick overview, I construct a non-abelian version of Stokes' theorem, which is slightly different from one that some people have been using, for example, Professor Cundy, which naturally leads to a Abelian decomposition. And we find an exact equivalence between the Wilson loop of the non-abelian theory and of the abelian theory, and the Wilson loop is a measure of the static quark potential, so it measures the potential between the two quarks. And this means that you can use this abelian restricted theory to investigate quark confinement, and it turns out to be a much easier issue to solve. And because there's an exact equivalence, if you can solve quark confinement in the abelian theory, you've also solved it in full QCD. And what I will hopefully suggest, if I get time, is that certain topological objects within this restricted theory may partially explain quark confinement. So what about this gauge invariant? I'll discuss what I mean by gauge invariant a bit later. Abelian decomposition. This was originally proposed by Cho on the basis of work by Duran and Gay, and there's also work by Fadif and Niemi and a few other people later on, back in the 1980s. This started. So we start by choosing a field theta within SUN across space. My only requirement is that this field is going to be of a differential of this field with respect to space exists, of my only requirement at the moment. I then construct a rotation of the Gell-Mann or Pauli matrices, and I select from these the abelian directions. So I'll be mainly talking about SU2 in this talk, so that's N3 or lambda 3. We then split up the gauge field A mu into two parts. A hat mu, which is going to be our color neutral part, and X, which contains the color gluons. These are defined by the differential of N with respect to the A hat field being 0, and the trace of N with respect to times X mu is also 0. And there's a known and unique solution to this in the continuum, which I've given here. I'll be talking about this solution a little bit later, but for the moment, I'll just say there's a known solution in the continuum for A hat and F. In particular, you should notice the field strength is just proportional to this Nj or N3. In other words, it's proportional to lambda 3, which is diagonal matrix, so this is basically an abelian theory. So now I'm going to quickly discuss lattice QCD. We had a good talk yesterday, so I'll skip over this. I'm using epsilon rather than A for the lattice spacing. It's defined in terms of a gauge link here, which is represented by the path-ordered integral of gauge fields between the two lattice sites. So a simple covariant derivative, we multiply the fields by the gauge link, subtract fields at the original site, and otherwise it's a standard differential. This is very naive, and not really usable in practice, but give you an idea. So we're going to rotate to Euclidean space-time, first of all, and consider a curve a rectangle in the xt plane. I'll use sigma to parameterize the position along the curve, and the Wilson loop is given by the path-ordered integral of the gauge fields around this curve, which you can also write in the lattice theory as the product of the gauge links going around this curve. And the trace of the Wilson loop at large times just gives you the exponential decay of the interquark potential. So this is what I want to be measuring and what I want to study. I've examined both SU2 and SU3 Yang-Mills theory. I'm going to give numerical results in SU3 a little bit later. The theory is in SU2 I'm presenting because it is much simpler than the theory for SU3. It's the same basic principle, but for the sake of writing the equations on one line rather than one slide for each equation, I think SU2 is easier for a talk. So I'm going to proceed by, I should say the main problem with this is the path ordering. It's non-abelian theory, so the path ordering makes this difficult. If this were an abelian theory, of course, you wouldn't have this path ordering, and the issue would be relatively straightforward. You could just convert this into an integral of the field strength. So my aim is going to be just to change this into an abelian function. And the way I'll do this is by introducing a field theta within SU2 in this case, and I'll write this as an identity. I'm just introducing theta, theta dagger at each point in the Wilson loop. And I'm going to choose theta so that for those gauge links which contribute to the Wilson loop, this term is diagonal. And there is a solution to this. It corresponds actually to the eigenvectors of the Wilson loop. And that means theta is unique up to the ordering of the eigenvectors and a Euron phase for each of them. This means we reduce our Wilson loop to this form here. And this thing here is nice and abelian and can be treated relatively easily. I'll tell you what U hat is a little bit later. So what this means is we have removed the path ordering and we can then proceed a lot easier. So I'm going to generalize this theta across I've talked about one Wilson loop. You can nest various Wilson loops, stack them up in the other directions and define a theta field across all space-time. I'm going to also introduce a field U hat, so that for all gauge links, theta dagger U hat times theta is diagonal. Obviously, you can't do this for the U field because you can only do this in one direction effectively, or one subset of links. But to define this U field, I'll link it to the actual gauge fields by fields, which I'm going to call X hat, for some fields X hat. And we can write the U field as basically the exponential of the gauge field up to orders of the lattice spacing squared or cubed. Then you can expand the equation I just wrote on here, X hat U hat equals U, and you get this light mess. One reason I wanted to highlight this is because there are three terms here for this U hat, of this small U hat, and I'm going to set this first term here to 0, which gives me a certain freedom. So I'm going to have trace of n3 x dagger minus x equals 0, where n3, as before, is given by theta lambda. It's just a rotated Gell-Mann matrix. So I've had these three equations defining U hat and x, and if you look at it up to lattice artifacts, these are exactly the equations of the abelian decomposition I mentioned before. For gauge transformations, this is the standard gauge transformation of a lattice field. Theta transforms this way from the definition I've used for the Wilson loops, and then you can plug these gauge transformations into these defining equations, and you discover that U hat, in particular, transforms in the same way that the U field does. There's an extra U1 factor coming in here. So paths of gauge link constructed from U hat are gauge invariant. This also, smaller U hat is also gauge invariant, follows from this, gauge covariance. And what this means in particular is we can construct a new field theory just by replacing U with U hat for all observables, and that will satisfy gauge covariance and all the other symmetries we want for the theory. So this restricted QCD will be confining with the same string tension as full QCD because the Wilson loops are exactly the same. Thanks, I'm running very slowly. So if we can explain confinement in restricted QCD, we've explained it in full QCD. But because this is essentially an Abelian theory, it is going to be much easier to work with. I should also say the colored X field does not contribute to confinement at all, which is important. It means just the Abelian terms contribute to confinement. So this is the known solution for A hat and F. I've written it in a slightly different form. They depend on two terms. One term here, which I'm calling the maxwell term. I should say this object in the trace is this small U hat that I've been talking about as the diagonal term. It depends on the Maxwell term and also a term that is dependent on theta. I'm going to parameterize theta in a particular way, which is perhaps not so clear here. I've taken out the U1 factor at the end and put theta equals e to a phi. Theta tangent theta you can calculate, it gives this. I'll come back to this later. And this term here in the field strength, which I'm calling H, which will become important, you can also calculate in terms of these parameters A and C. So I want to use Stokes' theorem, convert this line integral into a surface integral. This is valid everywhere except where there's a singularity. There are three main sources of singularity. Firstly, when the Wilson loop has degenerate eigenvalues, this is not actually important in practice. Secondly, when the gauge field is discontinuous, this means you need to be a bit careful when choosing your gauge, but it's also not so much a problem. Or there you can have a topological singularity, which is what I intend to quickly discuss in 2 minutes over 10 slides. So theta was written in this form. You can see that C is ambiguous when A is 0, A is pi over 2. This means in principle you can have some winding around these points. So if I map A and C to particularly the xt plane where I've put the Wilson loop, there are various different types of topological object of interest. You've got a Ranu monopole. I'm going to be focusing more on this pi1 object, which has C proportional to this angle between x and t. They're integer winding numbers. They are invariant under gauge transformations or deformations of the gauge field. So U hat, this is the form for U hat. We've got theta staggered d mu here. Stick this together, and we get U hat has got a Maxwell contribution and an integral over sine squared A d mu c. So if the integral of this around the Wilson loop gives some Maxwell term, it gives this term in red here, which is proportional to the winding number times pi. And then this term here, where sine squared A minus half fluctuates, so this is going to just give you a boundary term. It's going to be relatively unimportant on large Wilson loops. I'll skip this slide. So what can we do with this? We can calculate the field strength and then compare it with the lattice simulation. So we can work out what the patterns for field strength are going to be for each object. Monopoles, you've got nothing in the AX field and one-dimensional lines of high field strength. This is a four-dimensional theory. It's a point-and-arc charge, so going like 1 over r squared in the spatial directions, but also in the time direction, it's continuous. Or you can rotate the coordinate directions to change them around. These pi1 objects, on the other hand, and I seem to be losing the battery on the pointer, can be one deep lines, but the important thing, they've also got points in the EX field as well, so you can distinguish between these two types of topological objects by looking at the field strength. And these are some plots in a slice onto the lattice in the XT plane. They're contour plots. These are, the red ones I think are positive field strength, the purple ones negative field strength. We see that the field strength, F mu mu, lines up, at least in the XT plane, and the other directions as well, with those predictions which you can construct from the theory just by looking at these structures. And it confirms the one-dimensional, the lines in the expected directions. It basically all matches what I was expecting in the theory. And I should say, if these are present, I won't consider this a proof that they're present, then you would have confinement. The next question is, how much does this dominate the string tension? Well, it's possible to separate out the topological of this theta term from the rest of the A hat field on the lattice. I just do this in one particular way. For other ways, you can do it. So what I'm looking at is the ratio of the string tension from the topological part to the string tension of the full part of full QCD. And if this ratio is 1, then confinement just comes from this theta term, and perhaps the topological objects I've been describing, perhaps some others that are in there. Now, we did a few quick and dirty calculations before this, and this ratio came out at about 0.9, but they weren't exact. So I'm just showing you here the result of the exact calculation, which is unfortunately not as good as I like. So here, this is the plot. The red and pink or purple points are the restricted and full gauge fields. So this is basically the potential against R plot. And these are lining up exactly as you would expect. The topological part, unfortunately, is not lining up with the same string tension. In fact, it comes out at about a factor of half of the string tension. So this means that I've explained half of the string tension in full QCD. There's still 50% missing, unfortunately, which I need to think about. This is relatively constant as we change the lattice spacing and also the volume. I'm out of time, I know, so I'll come to the conclusions. So we've proposed a new model which in principle explains the area scaling of the Wilson loop and why mesons are color neutral. It can be examined both numerically and theoretically. The field strength backs up the model, what I'm expecting. The theta term, unfortunately, only contributes to half the string tension. So I've got half of the confinement explained possibly by this model if I haven't made a mistake. Possibly this is a lattice artifact, or possibly I've done something wrong somewhere. So I'm checking my last calculation with other methods currently. Or possibly you've got a contribution also from the Maxwell term contributing to confinement, and I'm currently looking into this and seeing if maybe some center symmetry can give you something. But in any case, this choice of decomposition seems to be a natural and relatively easy and elegant way to study the problem of quark confinement. Okay, thank you.
Questions?
Yes. Okay.
That what you didn't mention anything about quantization. Is this pure classical, your calculation?
No, this is, I mean, all we have talked about here is classical, but you can generate this from one configuration to another. I'm currently, I have figured out, I haven't talked about the quantum theory, I haven't talked about the measure, for example, and how you can do that. But this is a lattice simulation on one gauge configuration. You can average it over numerous different gauge configurations generated with the action. You can write the action in terms of these parameters I've written down to perform a path integral.
So, in more detail later.
Yes, okay. But I can write this down in a path integral formulation of this theory in a path integral formulation. Although that's not yet published, that's still a work in progress. Yes.
Any other questions?